Hi everyone. The topic of my presentation today is mapping IoT applications on the edge to Cloud Continuum with a filter stream model. So IoT is gaining popularity in many scenarios, such as transportation, healthcare, and the smart environment. So as more and more devices are connected, multi-layer wireless networks are becoming a common topology. So here shows an example. The cameras and the smartphones in the example are connected to the edge devices, and the devices are also connected to the cloud for further processing. So while using such topology for the deployment of IoT applications, the computation, input data, and the communication should be managed. The computation means the processing tasks within the application. So different deployment plan assigns different processing tasks on different places, so which may cause different latency. So same for the input data. And also, the communication cost should also be considered because of limited bandwidth in the network. So the motivation of our work is that first, we want to reduce the latency time in such topology. Second, we want to implement the automatic partitioning of the computation stages along the path from the edge to the cloud. Last, we want our solution suitable to the increasing number of layers and heterogeneous environment. So however, many challenges exist in our work. First, nodes with limited computation ability should be organized and managed. The limited communication speed can also affect the decision of best deployment plan. Second, the application latency is also an important consideration. Third, the data arrival rate and application requirements can vary over time, so that our solution should be able to adapt to such dynamic changes. So in general, there are several contributions have been made in our work. We designed a framework helping deploy the computations automatically and dynamically. Second, a cost-based deployment algorithm is developed. Also, a power model is built in our work. At last, 3 common streaming IoT applications have been implemented and evaluated in our work. So we propose a framework called Actor Deployment Framework. So there are 2 types of components in our design, the station and the provider. A station is any device that produces the data, such as sensors and mobile devices, or the middle-layer devices such as IoT gateways. A provider is a powerful device that serves as a backend, such as the cloud. So in our design, the streaming application is deposited into a series of independent actors, which is referred from Kelvin work. An actor represents a computation or a service that can only communicate with others by passing data messages by port. Actors can only be triggered by streaming blocks of data or event notification. And also, each actor is self-contained and can hide its internal state from the rest of the application. So there are 2 kinds of modes in our system, deploy mode and running mode. So the deploy mode includes service management and deployment management. The service management is to profile and manage actors both on stations and provider. It includes service profile and performance profile. So the service profile will include the code of all actors and their order in the pipeline, and the performance profile will log the performance analysis locally, including the execution time and the transmission time. So when each station finishes its service management, the deployment management starts to work to obtain the optimal decision with our deployment algorithm and dispatch the decision to all stations. So since the application is deposited into a series of independent actors, so the goal of our deployment algorithm is to specify where each actor should be executed. So in a given pipeline of actors, our algorithm will find a fixed number of partitions for the application deployment problem. And the number of partitions is just the number of possible deployment places. So the cost function in our deployment algorithm is shown like here. There are two important considerations: latency and energy. The latency includes processing time and transmission time. Each station and provider has its own local time, which is the sum of time spent on the processing locally and the transmission time to the next layer. So in the equation of local time, three situations are discussed here. So when the J is equal to N, it means the local time in the provider. So the transmission time is 0 in this part. Since the processing is done in a pipeline fashion, so the overall latency is determined by the maximum local time among all stations and provider. For the transmission time, we simply use the linear relationship equation with the size of data transmitted and the transmission bandwidth to describe it. So another key consideration in our deployment algorithm is the energy. It is determined by the power consumption rate and the time over which the processing and data transmission occurs. So in its expression, it includes both the local processing power consumption and the transmission power consumption. So suppose we have a pipeline of actors from Act 1 to Act M. So the deployment problem is an optimization problem to find the minimum cost, which can be solved by forward dynamic programming, which is used in our work. So here, T cost ijk means the local time cost when deploying the actor AI to AJ on case deployment place. So when I is larger than j, which means there is no actors deployed in the case deployment place. So there is no processing cost in this place. E cost j means the energy consumption from Act A1 to AJ data deployed into the extreme device. So another important symbol is cost ik, which denotes the minimum cost of deploying the actor AI to AM in the last k deployment places. So our final goal is to compute cost 1n that denotes the minimum cost of deploying all actors in n deployment places. So three situations are discussed in our algorithm by using forward dynamic programming. Here we only consider the energy consumption in the first layer. So when k is n, the actual energy consumption is added in the cost function. In our experimental setting, a 3-layer network is built for our application. 2 Raspberry Pi play the role of stations and are connected by a wireless local area network. And a desktop computer plays the role of a provider in our system and is connected to one station by a local area network. In our baseline, the edge devices push all input data to the provider directory, and the provider performs all processing tasks. 3 streaming applications have been implemented and evaluated. The first application is convolution neural network, and we designed 9 actors. The best positioning of CNN application is that the first 3 actors be deployed in the first Raspberry Pi, and all other actors are deployed to the desktop computer. Our second application is fashion landmarks, which is deposited into 5 actors. Based on our algorithm, the first 2 actors are deployed to the Raspberry Pi in the first layer, and the third actor is deployed into the Raspberry Pi in the second layer, and the last 2 actors are deployed to the desktop computer. The last application is traffic situation management, and we designed 8 actors for this application. The best position is that the first 2 actors be deployed into the first Raspberry Pi, and other actors be deployed into the desktop computer. The figure shows the relationship of response latency between our solution and the baseline. The CNN application, you can see that achieves 95% latency reduction, and the traffic situation management achieves 61% latency reduction. But for the fashion landmarks application, response latency is around the same as the baseline response latency. The main reason is that the fourth actor of this application that deployed in the provider that takes more than 99% of total computation time. So the figure here shows the power consumption in the edge device using our framework compared to the baseline solution. So all 3 applications achieve good results, especially for CNN application. The main reason is that in the baseline solution, the entire video data is transmitted to the provider node, requiring a large amount of power for the transmission. However, in our solution, edge nodes perform a subset of actors, resulting in a large reduction of amount of data required to be transmitted. So in conclusion, in this work, a new nuanced framework is designed for mapping IoT applications with a filter stream model. Also, a dynamic programming-based deployment algorithm is developed. The implementation and evaluations of 3 IoT streaming applications show the benefit of our solution, which show greater reduction both on latency and power consumption. Thank you for your attention.